Welcome to CSEGuru. In this session, we will discuss knapsack problem using branch and bound technique. Already, we have discussed knapsack problem using greedy technique and dynamic programming technique. Now, we are going to discuss the knapsack problem using branch and bound technique. We can solve this knapsack problem using branch and bound technique with the help of the construction of state space tree. Now, what is knapsack problem? Given n items of known weights, the weights are nothing but W1, W2, W3 up to Wn, any number of weights they can give, and profits P1, P2, P3 up to Pn. For corresponding weight, the profit will be given. Okay, so given n items of known weights and profits and a knapsack capacity M. So this knapsack capacity represents the maximum capacity of the knapsack. So you can choose and place the items into the knapsack such that it should not exceed the maximum capacity of the knapsack. So with the given weights, profits and the maximum capacity, it is required to find a subset of items. So here among these items W1, W2, W3 up to Wn, among these items, we can choose the subset of items. Any subset we can able to choose such that it should not exceed the maximum capacity. So we can choose and place the subset of items into the knapsack that fit into the knapsack. So that is our problem. And here the main objective is place the objects into the knapsack so that it should attain the maximum profit. That is, it should earn maximum profit. And the weights of the object chosen should not exceed the capacity of knapsack M. So what is the maximum capacity they have given? It should not exceed the maximum capacity because the bag will not fit. Okay, that is the meaning. So here we need to choose the items to place it into the knapsack such that profit should be maximized and also it should not exceed the maximum capacity. So this is nothing but knapsack problem. So the problem can be stated as maximize I equal to 1 to n, pi and xi. That is, the profit should be maximized. Subject to the constraint, summation I is equal to 1 to n, wi xi should be less than or equal to m. So this m is nothing but knapsack capacity. Okay. So here maximize the profit and it should not exceed the maximum capacity. The items we are choosing to place it into the knapsack should not exceed the maximum capacity. Okay. So this is nothing but the knapsack problem. And here x represents the solution vector consisting of either 0 or 1. So 0 in the sense we are not choosing that particular item to place it into the knapsack. 1 in the sense we are choosing that item to place it into the knapsack. So that is nothing but x. So here to solve this knapsack problem, it is convenient to order the items of a given instance in decreasing order. So the items we should arrange in decreasing order by their value to weight ratio. So here for every item they have given, we need to find value by weight ratio. That is value divided by weight in the sense we will get a ratio. And this ratio we have to order in the format of decreasing order. So it helps to solve the problem easily. And here, if you are considering the knapsack problem, here we are going to implement branch and bound technique to solve knapsack problem, right? And this branch and bound technique we will implement with the help of the construction of the state space tree. Already in branch and bound technique, we have discussed two problems. One is traveling salesman problem and assignment problem. Now this is the third problem, that is the knapsack problem. Under branch and bound technique, all these problems, traveling salesman problem, assignment problem and knapsack problem can be implemented with the help of the construction of state space tree. And here for knapsack problem, how we are going to construct the state space tree? See here in branch and bound technique, the traveling salesman problem and assignment problem, there is a unique method to construct the state space tree with few steps. For each problem, the construction of state space tree is unique in branch and bound technique. Okay. So to solve the knapsack problem, we need to construct the state space tree by following these steps. So first, construct the state space tree as a binary tree. What is binary tree? Binary tree is nothing but tree with two subtrees, only two subtrees, okay, left subtree and right subtree, or otherwise this is a left child and right child. So here for knapsack problem, we need to construct the state space tree as a binary tree. But in assignment problem and traveling salesman problem, it is not the case. We will construct the state space tree with more than two subtrees, okay, but here in knapsack problem, it is a binary tree. And here each node of the tree on the ith level, where I equal to 0 to n represent all subset of n items consisting of the selected items, okay, that is 0th level, first level, second level, if it goes on in the sense that each level represents the subset of n items consisting of the selected items, that is the items we are selecting to place it into the knapsack. We have considered that items, okay, that is the meaning. And how this selection happens in the sense, a selection is determined by a path from root to the node where a branch going to the left indicates inclusion of the nth item. See here, if this is the state space tree in the sense, see the branch going to the left indicates the selection of that particular item to add it into the knapsack, okay. Inclusion of the next item, that is the meaning. So left side, if you are adding any node in the sense, meaning is we are including that item into the knapsack. Branch going to the right indicates exclusion from the solution. If any item is added as a right subtree in the sense, that item will be excluded from the solution. So for a particular selection, record the total weights and the total profit V in the node along with the same upper bound. So we need to register the weight and its profit along with the upper bound value. So the upper bound value, how we are going to calculate? That is, the upper bound value can be calculated using the formula UV is equal to V. V represents the value of the item plus M minus W. So this M represents the maximum capacity of the item and W represents the weight of the current item. Okay, that particular item we are going to consider right now. Okay, and then Vi plus 1 by Wi plus 1. That is the value by weight ratio of the next item we need to consider. Okay, that is I plus 1. Value by weight of the next item. Okay, and here W represents the total weight of all the objects placed into the knapsack. And V represents the total profit or value of all the objects placed into the knapsack. Okay. So these are all the steps we need to consider to construct the state space tree. So the main thing what you need to consider here in the sense, so first step is construct the state space tree as a binary tree, only with two subtrees. Meaning is a tree with only two subtrees. Okay. And we can able to add the item into the knapsack as a left subtree. Meaning is that particular item, if you are adding in the sense, that will be considered to place it into the knapsack. So the left subtree, if you are considering in the sense, it will be growing. If you are considering that particular item, next level, we will add that item. Okay, that is the meaning. And whatever the tree we have mentioned as a right subtree in the sense, that particular item, we will exclude from the solution. That is, we are not going to consider that particular item to place it into the knapsack. Maybe it violates the problem constraint. If you are adding that particular item, it will exceed the maximum capacity or it will not maximize the profit. Okay. So anyway, if it violates the problem constraint in the sense, in that case only, we will exclude that particular item. And that particular items, we will mention it as a right subtree. So left subtree, inclusion of the item, right subtree, exclusion of the item. Okay. And here, whenever you are considering that particular item, we need to register its weight, value and upper bound. And upper bound, how we are going to calculate in this is the formula. Upper bound is equal to V plus M minus W into Vi plus 1 divided by Wi plus 1. So this is nothing but the value by weight ratio of the next item. Okay. So with these steps, we are going to solve a problem in the next session with the help of the construction of the state space tree. Thank you for watching this video.